So any doubts from yesterday?
No, ma'am.
Okay, so today we are starting with a new unit on POSets. Since all of you have
Ma'am,
seen,
can you let me in another device?
sorry?
Can I join from another device?
Yes.
Can you just allow me?
Yeah.
Yes, ma'am. Yes.
Okay.
Thank you.
All right. So no questions from the previous part as yet. Then I'll start with the new topic. So since you people have seen only just a bit of POSets, I mean others have not responded, so I'm not sure if they have seen POSets or not. So we'll start with a very small recap of POSets, and actually that also only the things which we would need for the current setup, and we'll keep proceeding. All right.
Okay, ma'am.
So is my screen visible now?
Yes, ma'am.
Great. So as you people have a little idea, POSets it's a set which comes with a partial order. Okay. So what does it mean to have a partial order? Is that given any two elements in this set, these two elements may be comparable, may not be comparable. So either when you have two elements x and y in the set P, there is a possibility that x is less than equal to y, or y is less than equal to x, or there is no relation between x and y, right? So that is what a POSet is. And whenever for two elements there is a relation, you say that the two elements are comparable. If there is no relation between them, you say that they are incomparable. Okay, so just to keep things simple, we'll interchangeably use all these symbols, as x less than equal to y would also be rewritten as y greater than equal to x, even though this is actually a operator, right? It's a binary operation
Yes, ma'am.
which takes two elements and yields a Boolean output. But here we'll use this as we have actually seen it or understood it as operations on natural numbers, sort of, where you can compare and figure out which one is larger, which one is smaller. So less than equal to, strictly less than, exactly equal to, etc. All these things we'll be using just as how we understand in our common sense. Okay. So assuming that now we'll start with the definitions which we need. So if you take two elements in P which are comparable, and suppose that x is less than equal to y, then you can define an interval in the POSet denoted by xy, close bracket xy, and it collects all those elements which are in between x and y, including x and y. Okay. So this, as it may even look like from the real analysis, it's a closed interval, but now it's a closed interval in P, the POSet. Okay.
Yes, ma'am.
Okay. Similarly, once you have a closed interval, you can also define an open interval. So open interval will collect all the elements of the POSet which are strictly bigger than x and strictly smaller than y. Okay. So elements in this chain, but excluding x and y. So something like this is an open interval in the POSet P. And by convention, empty set is not a closed interval. So empty set you can achieve here through an open interval by putting open bracket x comma x close bracket, close as an round bracket. Okay.
Yes.
But here you do not allow that. So whenever you define the closed interval, you assume that x is less than equal to y. All right.
Yes. Ma'am, here, what does the less than sign mean?
Less than
Uh,
sign means that x is less than equal to y in the poset.
no, in the second definition of open interval, the
Same thing.
strictly less than sign.
Strictly less than means that x is less than equal to u, but x is not equal to u.
Yeah. Okay. Okay.
Okay, just as you would try to understand from the common sense. You have
Yes.
u to be strictly bigger than x. So u is greater than equal to x, but u is not equal to x. And for this side, u is less than equal to y, but u is not equal to y. Okay.
Yes.
So that is why in the beginning I said that we'll be using the less than equal to interchangeably with greater than equal to by swapping the two sides. And we'll also be using strictly less than symbol, which appears here, strictly greater than symbol, which you can try to see from here. If you swap the two elements u and y, and the symbol equal to. Okay.
Okay.
So with these things in place, now you say that some poset P is locally finite if all of its intervals are finite. Okay, so this interval in particular is collecting some elements of the poset, right? So the collection this which you get here as a set, if this is finite, then you say that this interval is finite. And if all the intervals are finite, the closed as well as the open intervals, then you say that the poset is locally finite. Each of its interval is finite. Okay. So
Okay.
now in what we are going to do, we will consider only the closed intervals. So I will not mention and now on that we are dealing with a closed interval, but whenever I say interval, it would mean that we are dealing with a closed interval. Okay.
Okay. Yes.
So let's define the int p to be the set of all closed intervals of p. Okay. So I have written closed here, and after this, I would simply drop the word closed, and interval would mean the closed interval. All right. And if k is any field, then you define f from int p to k as a function. And since it's int p, which means the element here is an interval, right? So
Yes.
it should be written as f round bracket inside that close bracket xy. But to simplify the notation, we would simply write this as f of round bracket xy. But don't confuse this with a open bracket xy. Okay,
Yes, ma'am.
we are going to deal with only the closed intervals, and this is just a simpler short form for this to avoid writing more.
Okay, ma'am.
So the incidence algebra of P over the field K is denoted by I of Pk, which we will write simply as Ip, because field we are fixing once and for all to be K. Okay, then this is the algebra, K algebra of all functions f from int p to k. Okay, where the multiplication is given by, so multiplication of what? Two elements here. So two elements in this K algebra are two functions of this type. So you take two functions f and g. They are going to act on closed interval SU, let's say. So on an interval, how they act? They take the convolution, which means you take an intermediate element and then you take the product of those two. So f of st is an element in K, g of tu is an element in K. So this product is taking place in the field K. Okay, so you take product of all these pairs where this T runs over the set, the interval S comma U, and then you add them up. So
Do
this
we
is how.
assume that this is locally finite P?
Yeah. So we have fixed here that it's locally finite. P is locally finite.
Okay.
Okay. So incidence algebra I'm defining for locally finite.
Yes.
Yeah. So Fg of Su is defined to be the sum of these products f of st, g of tu, where t belongs to the interval s comma u, closed interval s comma u. So as I already said, so since p is locally finite, you know that this particular occurrence of t is finite. There are finitely many t's which lie in the range of s and u, and thus this particular sum is also finite. So it makes sense to define fg, the convolution of these two functions, in this manner. Okay.
Yes, ma'am.
Now we can also see that IP, the incidence algebra of P over K, is an associative algebra, which means you have associative law, and same you would define it f, g, and let's say some h. So then you would take g and h, you would have run from elements between s and u, and then you would put another thing. So it's like dividing the interval su into three parts, right? And which,
Yes.
if you take the first two parts first or the last two parts first, would not make a difference as long as the ordering remains same. So associative algebra structure is there on IP, and it has a two-sided identity which we denote by delta or the symbol 1, but mostly with delta. So delta of ST you define to be 1 if and only if S is equal to T. Okay. So it's like what you also seem to have, like characteristic function. So it gives 1 only when S is same as T and 0 otherwise. All right.
Yes, ma'am.
So another interpretation of IP can be through the elements it has. So how you can extend this is that if you have two intervals, let's say ST and UV, and you would want to understand if there is a way to conjugate, or rather concatenate these intervals. So when is that possible, and if it is possible, what does it give you, is the next question. Because if, let's say, you have the close interval 1 2 and close interval 2 3, then you would really want to, if you want to see the elements in this, it is equivalent to seeing elements in the close interval 1 3, right?
Yes.
So similar thing we want to do here. But since we said that int p is what we are going to deal with, int p means it's the collection of closed intervals. So for instance, if you take 1 2, close interval 1 2 and close interval 4 5, then I cannot make these two closed intervals into a single closed interval, right? Because there is a chunk from in between which is missing. Correct?
Yes.
Precisely the open interval 2 to 5. If the close interval 1 2 and close interval 5 6 were given. So when does it make sense to talk about concatenating two intervals into one interval, is what we are doing here. So you define the convolution, which is uniquely defined through, you take the interval st and the interval uv, then their convolution is SV if T is U. That means its last element is the first element of the second interval, and it's 0 otherwise. Okay.
Okay.
And now with this bilinearity, you can extend it to the entire of IP. Okay, IP, remember, it's a collection of all the functions from int p to k. So you would have already had a function from f, let's say from st to k, and then you would have had a function g from uv to k. But now st and uv becomes sv. So there is going to be a function h from sv to k. But now this function from sv to k should in some sense make sense in the terms of f and g, which were defined here, right? So that is what we are talking about, that you can extend it to the whole of IP by linearity using this convolution, right?
Okay.
So any f in IP is identified with expression of summation f of st, close bracket st, where st belongs to int p. Okay. So any f, when you say that you are not really, you do not give any input to f, just f means that f of st is applied, and you take the summation of all such fst's where st is the close interval coming from int of p. Okay, so if f belongs to ip, then as a function f, it has a, so all these four properties are equivalent to each other, and f has a left inverse if and only if f has a right inverse, which is equivalent to saying that f has a two-sided inverse. And when this is equivalent to this and this is also equivalent to this, it is quite straightforward to see that as soon as they are equivalent, you know that the two-sided inverse is going to be the unique left inverse as well as the unique right inverse, right?
Yes, ma'am.
Yeah. And all these conditions are also equivalent to saying that f of tt is non-zero for any t in the poset P. Okay.
Yes.
So these conditions in some sense tells me what I should expect from here, but what is the main crux of this particular proposition is the fact of equivalence of these two conditions, that f has a two-sided inverse if and only if f of tt is non-zero for every t in P. So this is what we like quite often use later. Moreover, if f inverse exists, then f inverse of SU depends only on the poset SU. That is only on this portion of the poset. When I write poset SU, poset closed interval SU, you understand this is a subposet of the original poset, which is having induced operation. The partial order is induced from the main poset, and then this is a subset. Okay.
Yes, ma'am. Ma'am, can you show the multiplication once more?
Yeah. So FG
Yeah.
of SU collects all the in between T between S and U, and then you, so whichever is the first one, you take F, if this is the first one, F of ST, and then it is followed by G of TU.
Yes, ma'am.
Okay, so this is what you have to just remember. And
Yes, ma'am.
this comes from here. Okay, so T in between is running over all the T's which are sitting in between S and U. Okay.
Okay, ma'am. Yeah.
Okay. So this we have seen. Now we see some useful functions on the incidence algebra. So we first define the zeta function. So xi of tu is defined to be 1 for every t less than equal to u. Okay.
Okay.
So since we said that empty set cannot be written as a closed set, it means that you always have, whenever you write close bracket s comma t, you are assuming s is less than equal to t, right? Otherwise it will become empty.
Yes, ma'am.
So in that fashion, when you now see the function, any function f from the int p to k, you also assume that the interval, intake interval, whichever I will choose from int p is going to look like of the form st with which has s less than equal to t. And therefore, I care only about such elements. So zeta of tu, the definition being defined only for t less than equal to u suffices. This definition is complete here.
Yes, ma'am.
Able to see this?
So on all closed intervals, it will be 1.
On all the closed intervals, it will be 1, right?
Yes.
Okay, so this is your zeta function. Now, if you take convolution of zeta function with itself, what do you get? So you do zeta square of SU, that's going to be zeta zeta of SU. But by definition of convolution, what you write this is the summation of zeta of ST, zeta of TU, the product of these two functions. And then this sum runs over all the T which are in between the elements S and U, right?
Yes, ma'am.
So zeta, since it is running over T which is greater than equal to S, zeta of ST is 1 by this definition.
Yes.
And also T is less than equal to U, so zeta of TU is also 1, again by the same definition.
Yes, ma'am.
So whenever T is lying between S and U, both these elements are 1. Therefore, what you actually have is that it's a summation of ones. How many times? For all the occurrences of T which are in between S and U. Correct?
Yes.
However, this is nothing but the number of elements which are there in the closed interval SU.
Yes, ma'am.
So that is what is written. Now we move to another function. So zeta square you figured out turns out to be like this. Number of elements in this set, in this interval. If I had taken zeta cube of SU, you would have applied zeta once again on this, and you would have had a zeta of ST1, zeta of T1, T2, zeta of T2U with S less than equal to T1, less than equal to T2, less than equal to U. Isn't that right?
Yes.
And that would have given you the number of occurrences T1, T2 would come in between S and U with additional property that T1 is less than equal to T2, right?
Yes, ma'am.
So that is same as saying that how many elements or rather, how many sequences of length 2 are there in between S and U? Sorry, 3. 2 elements you counted here itself. Length 2. S to T is length 1, T to U is length 2. Right?
Yes, ma'am.
So when you do a zeta cube, you are actually computing the number of chains which are of length 3 from S to U. You would have had a S to T1 length 1, T1 to T2 length 2, T2 to U length 3. Right?
Yes,
So if you keep on proceeding in this manner, what you can in general write is that for any k in natural numbers, the zeta k of SU is summation of 1 running, summation of 1, and this summation runs over this entire sequence. So S I just relabel as S0. So S0 less than equal to S1 less than equal to S2 and so on less than equal to Sk, which is the final element, which is U. So it's the number of multichains of length K from S to U, right?
yes, ma'am.
Great. And now, once you understand this and remember this definition and the definition which we gave here, okay, so delta ST, as we said, will denote the identity to be either by delta or by 1. Now you compute zeta minus 1. So zeta of SU is 1 if S is less than equal to U. 1 is identity, which means it is 1 if and only if S is equal to U. Right? So since you already have the condition that S is less than equal to U, either S is strictly less than U or S is equal to U. Those are the two subconditions.
Yes, ma'am.
So when S is strictly less than U, still your zeta is going to give value 1. But your identity morphism is going to give value 0. Right? And since this is an algebra, zeta minus 1 of SU is zeta of SU minus identity of SU. So zeta of SU turns out to be 1 when S is strictly less than U, but identity of SU is 0. Therefore, zeta minus 1 of SU is 1 when S is strictly less than U. However, if S is equal to U, zeta evaluates to 1 as well as identity evaluates to 1. Therefore, it is combined value is 0. Right? Makes sense?
Yes, ma'am.
Okay, if the same thing you would do for zeta minus 1 raised to k, what would happen? So you saw that if zeta was 1, only when t is less than equal to u, zeta raised to k turned out to be the number of multichains of length k from S to u, which had S and u inclusive. Now you have a different function which evaluates to 1 only when S is strictly less than u. Therefore, zeta minus 1 raised to k of SU is going to be the number of chains S equal to S0 strictly less than S1, strictly less than S2, and so on, strictly less than Sk equal to U of length k from S to U. Is that right?
Yes, ma'am.
You just have to notice when is it giving you the value 1. Or if you want to see it more concretely, you should try to do at least zeta minus 1 whole square applied to SU. Okay?
Okay.
So now another function which we see, and actually the last function for now, so 2 minus zeta. So 2 is identity applied to ST, and then the product is multiplied with 2. Okay? Or you can say identity applied to ST plus identity applied to ST minus zeta applied to ST. 2 you can write as 1 plus 1. But remember, these are not the numbers here. These are functions. All right?
Yes.
So recall again, zeta of ST is 1 for S less than equal to T.
Yes.
So if S is strictly less than T, what is zeta of ST?
That's still 1.
Hmm?
That's 1.
Plus 1. And if S is less than T, what is identity of ST?
0.
0. So you will have 0 minus 1. So that is minus 1. So 2 minus zeta of ST is minus 1 when S is less than T. Right?
Yes, ma'am.
Now, if S is equal to T, then zeta of ST is
That's 1.
plus 1. And 2 times of identity applied on ST is
2.
2. So you'll have a 2 minus 1, which is written here. Okay.
Yes.
So does 2 minus zeta, the function 2 minus zeta, which we have seen in IP, does this vanish for any point? For any interval of int p?
These are the only intervals. For any interval, S is less than or equal to T.
Right.
So it can't vanish.
Which means 2 minus zeta, in particular, if you apply to the interval tt, that is also non-zero. In fact, it
So
is
it
1.
will have an inverse.
So it will have an inverse by this proposition, which we saw. So f of tt is non-zero for every t of p. Therefore, it has a two-sided inverse. Okay.
Okay, ma'am.
So 2 minus zeta of tt is 1, which is non-zero for any t of p. Therefore, this function is invertible. What we want to claim is that its inverse actually is the total number of chains from S to T. See, now I'm not saying which length, I'm just saying total number of chains from S to T with the strict inequality here. This is my claim. So we will see two proofs of this particular claim. Okay, one is in a very sort of, to say, combinatorial or rather, what should I say, very manipulative proof, and the other one comes from topology. Okay, so let's start. So if let's say L is the length of longest chain in the intervals ST, then if you take the function zeta minus 1 and apply it L plus 1 many times to UV for any UV which are sitting in between S and T, then it's going to be 0.
Yes, ma'am. So here chain means strict inequality, right?
Yeah.
Okay.
Okay. So this is 0. Now you start manipulating with this function. Okay. So another thing, if you want to figure out what is its inverse, if you take the function 2 minus zeta and multiply it with some other function, let's say h, and if that product turns out to be the identity function, then you know that the function h is its inverse, as in h is the inverse of 2 minus zeta,
Yes.
because already by proposition I know that 2 minus zeta has a two-sided inverse and its left side inverse is unique, which is same as the right side inverse. Correct?
Yes.
So that's what we are going to do now. So 2 minus zeta you take and you take its multiplication with this particular function, which is given by 1 plus 1 as an identity, plus zeta minus 1 plus zeta minus 1 square plus and so on till zeta minus 1 raised to L. And this being applied on the element set interval uv, where u and v satisfy this. Okay.
Okay.
Now we further rewrite 2 minus zeta as 1 minus zeta minus 1.
Okay.
Then this factor along with this factor, it's easy to see that this is 1 minus zeta minus 1 raised to L plus 1,
Yes.
right? It's a raised to n minus b raised to n, or rather 1 minus b raised to n. We have seen this earlier also, this trick.
Yes, ma'am.
So this turns out to be 1 minus zeta minus 1 raised to L plus 1 applied on uv. However, zeta minus 1 raised to L plus 1 applied on uv turns out to be 0 for every uv which are in the range of st. Correct? So this is just delta of uv, right?
Yes.
Delta is the identity operator. Correct?
Yes.
So this becomes the inverse of 2 minus zeta.
Uh, but we have chosen UV inside this interval.
That's right.
So S and T were also arbitrary. Is it?
Sorry?
The S and T were they arbitrary or were they fixed before?
Your voice is not coming properly. What?
Sorry. Can you hear me, ma'am?
Huh.
So S and T, the
Huh?
variables,
Yeah.
like were they fixed before the proof?
Yeah. This entire thing is happening for that. So whenever you would do any 2 minus zeta, so remember 2 minus zeta inverse of st, you said that the claim itself is this is the total number of chains from s to t. So s and t are fixed. So you fix one particular interval and you say that when you apply the function 2 minus zeta inverse to this interval, it is counting the total number of chains from S to T, which means the initial point of this interval to the final point of this interval. Okay.
Oh, okay, ma'am.
So S and T remains fixed right from the beginning of the proof. And then you proceed further and you just take two elements in between S and T, which are U and V. U and V are variable. Depending on
So
which u or which v you choose, that is immaterial to me. All I'm saying is that this holds true for any u and v which satisfies this. Okay, so in particular, this holds true even for u to be s and v to be t.
yes, yes, yeah,
All right.
yes, ma'am.
Therefore, the inverse of 2 minus zeta, when restricted to int of st, not the whole int of p, but int of st, this is the inverse of this function.
Yeah, okay, ma'am. I didn't look at the last line. That's why I was.
You didn't let me reach there.
Sorry, sorry.
Okay. So you see that when you restrict yourself to int of st, then this is the inverse. But that is not really what we were interested in. We just wanted to understand what this inverse, when applied to a particular interval, counts. And now, if you see, remember what was zeta minus 1? What was the interpretation of this function?
Number of one chains, strict one chain,
Strict one chains. This was the number of
two chains.
two chains, and so on till number of, as in chains of length L, chains of length 2, chains of length 1, chains of length 0,
Yes, ma'am.
right? So when you write 2 minus zeta inverse applied to st is equal to this applied to st, you're automatically counting the number of uh, chains of different lengths. So in short, you're counting the total number of chains from s to t. And that is what we claimed here, total number of chains from s to t. And why I know that this is now a strict inequality here through this, because that is what my zeta minus 1 takes care of. You see, zeta minus 1 is non-vanishing only for s strictly less than u and not x s less than equal to u. Okay.
Yes, ma'am.
In fact, for any k, zeta minus 1 raised to k of su is non-vanishing only when you have a sequence of this pattern. S0 is strictly less than S1, which is going to be strictly less than S2, which is strictly less than S3, and so on. Okay, so this was the combinatorial proof where we had to actually restrict ourselves to the int st, but there is a topological proof also, and let's see what it does. So you define a topology on your incidence algebra by saying that a sequence f1, f2, and so on of functions would converge to a function f if for every s less than equal to t, there is some n0 depending on s and t such that fn of st is f of st for every n which is appearing after n naught. Okay. So after a large enough occurrences, after some finitely many functions have passed, all other functions of this sequence are evaluated to the same value as f would do.
Okay.
Okay. So
Yes,
if this is the topology I work with, then you again start manipulating this 2 minus zeta inverse and write it as 1 minus zeta minus 1 inverse. So if you consider this zeta minus 1 just as a variable, we know that this has a series expansion in this format. This also we have seen before,
yes, ma'am.
right? So this is summation zeta minus 1 raised to k, and summation ranges on all non-negative k's. So then 2 minus zeta inverse when applied on st gives you the summation of zeta minus 1 raised to k applied on st for k greater than equal to 0. But this is what? It's the number of chains of length k from s to t. Right?
Yes, ma'am.
However, this would vanish because the interval st is finite. P is locally finite. So this huge sum which you see as an infinite sum here actually terminates and has only finitely many terms, and those terms precisely give you the total number of chains from S to T. Okay,
Yes, ma'am.
so this is the topological version of how you can really deal with the entire thing without having yourself restricted to the int of one smaller interval. All right. So this is it. This is where our lecture ends for today. You have any questions?
No, ma'am.
Okay. Any other thing which needed to be discussed?
No, ma'am. This is fine.
Okay, then I'm ending the meeting. Bye.
Okay, ma'am. Bye, ma'am.